This video is an introduction to the topic of series. We want to understand what exactly a series is. We'll look at the idea of convergence versus divergence. We will learn specifically what a geometric series is, and we'll also see what a power series is. Before we get any further, I want to show you a visualization in Desmos that's sort of a spoiler alert about some things to come. But I hope it will get you interested in something that we're going to end up doing with this idea of series. What I'm going to show you is going to be a little bit confusing at first. It's not going to be obvious where I'm getting the things that I'm typing in, but trust me, as we progress through this section, we'll understand more of why things are working out as they are. I just want to give you a sneak peek of what we're going to learn later on. So I'm going to start by just typing in a polynomial here. I'll just call it f of x, 1 plus x squared plus x cubed plus x to the fourth. You can probably see the pattern that I'm making here. I'm just adding x to the fourth, x to the fifth, x to the sixth, and I could keep going. But one thing I want you to notice is that as I add more and more terms, the shape of the graph starts to look more and more like a specific shape. It starts to converge on some specific looking graph. Watch what happens as I add more terms. X plus x squared. Watch the shape. It starts to look like something specific. It zeroes in on a certain shape. So the shape that we're getting starts to look more and more like a specific thing. It looks like this polynomial is starting to match up with something. And I can tell you what it's matching up with. It's matching up with the function 1 divided by 1 minus x. Look how close that is. The function 1 over 1 minus x looks really close to this polynomial that we just plotted, especially when we're close to x equals 0. And as I take more terms for the polynomial will look more and more like that function. So this is a concept that we're going to explore in this section. We're going to see how polynomials will start to match up with certain functions, and we'll understand how to create these polynomials. Let me show you one more example that might be a little bit more interesting. I'm going to graph the polynomial x minus x cubed divided by 6 plus x to the fifth divided by 120 minus x to the 7th divided by 5040. Where are these random numbers coming from? Don't worry about that right now. But just look at this shape that we get. Look at this graph. Does that look at all familiar to you? Well, let me graph this function, sine of x. Look at that. This polynomial matches sine really closely from like -3 to +3. Basically from negative to positive pi, this polynomial looks really strikingly similar to sine. We'll see that if we were to continue this pattern, whatever it is, we could create an infinite polynomial that would be precisely equal to sine of x. That's something that we'll learn in future sections. So now, let's look at the concept of what a series is. By the way, those polynomials that we were just graphing, they're actually related to something called power series. What we were graphing are finite power series. So what is a series? A series is very simply a sum. It can either be a finite sum or it could be an infinite sum. So here are some examples. 1 plus 2 plus 3 plus 4 plus 5. There's a series. This adds up to 15. That's a finite series because it's just a finite number of terms. We can have another series here that could be infinite, like 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. And we could just imagine that this keeps going on forever. We can see the pattern. The next term would be 1 over 7, 1 over 8. And imagine just adding these up going toward infinity. That would be an infinite series. Writing out a whole bunch of terms like this gets a little bit bulky. And actually, if it's an infinite series, we can't write everything out. So we're going to see a shorthand notation for writing out a series like this. And perhaps you've seen it before. It's something called sigma notation. This symbol here is the Greek capital sigma. And don't be scared by this. I know it looks a little bit intimidating. This just means add things up. When you see this symbol, just think to yourself that that's telling you to add things up. It's simply a shorthand notation for a sum. So let's just imagine that we have a generic looking series here. We're adding up these a's, and the subscripts are just telling us that they're different a values. So a1, a2, a3. And we're imagining adding up infinitely many of these a's, whatever they happen to be. We can represent this infinite summation in this nice compact shorthand form by making this symbol, and then inside the symbol here we add a representative element that we're trying to add up. So the thing that's changing here is the subscripts, the 1, 2, 3. So we just say, let's use the subscript n, That's just a generic subscript. And then down below the symbol, this is telling us where the subscript starts. It starts at n equals 1. And then up above tells us where the subscript ends. We just keep going on toward infinity. And it's understood in sigma notation that the subscript will always index up by 1. So n starts at 1 and then goes up to 2 next, then 3. It's always understood that this index increments up by 1. So this is shorthand notation for this infinite series. I can write the sigma notation for these two series that I just wrote over here. This first one, I'm just adding up n. And n begins at 1, and it goes 1, 2, 3, 4, 5. So I put an n equals 1 down here, and up above I put a 5. And this is the sigma notation for this particular series. How about this series? It's an infinite series, so the sigma notation will be the sum. And what am I adding up here? I'm doing 1 over something. So I can write this as 1 over n. And here, n begins at 2, so I start with a different value for the index. So n begins at 2 and goes all the way to infinity. So here is the sigma notation for this infinite series. One important concept with the idea of series is whether or not a series converges or diverges. So this is an informal definition. There's a more rigorous way to define convergence. But we say that a series converges if it adds up to a finite number. If it doesn't add up to a finite number, the series diverges. So this first series that we wrote here, this converges. It converges to the value of 15. What about this series? If I add up all these numbers, does it converge to something? It seems, since we're adding up infinitely many things, that surely it must diverge. That's not necessarily always the case, though. We'll see some examples where we have infinitely many things added together that actually converge. In this case, this is related to something called the harmonic series, and this one actually does diverge. If you add these numbers up, it doesn't add up to a finite sum. So this idea of a series converging or diverging is going to be important as we progress with this topic. Let's work through some examples to practice these concepts that we've seen so far. For example 1, we want to use a heuristic geometric argument, whatever that means, to show that this series converges to 1. This is an infinite series, 1/2 plus 1/4 plus 1/8 plus 1/16. We're adding infinitely many things here. We can write it using sigma notation just like this. And I claim that if we add up these infinitely many numbers, they simply add up to 1. And we'll actually see that this is a special case of a very important kind of a series called a geometric series. And we'll see how to show in general that this sort of series converges. But for this example, I want to show you a really cool geometric proof that these numbers all add up to 1. So I'm going to draw a square. I'm going to draw a square with side lengths of 1. And I want to think about the area of this square. So it's a 1 by 1 square. If it's 1 by 1, then the area of the square must be equal to 1. So no matter what I do with this square, the area is always just 1. I'm going to chop this square in half. And I'm going to write in the different areas that I get. So if I chop it in half, on one side I have an area of 1/2. And then this other side here, I'm going to chop in half again. So I chop it in half. And one of these portions, that's 1/4 of the square. So that has area of 1/4. And then whatever's remaining, I chop in half again. So I take half of 1/4. Half of 1/4 is 1/8. Then chop this in half. Half of 1/8 is 1/16. Chop that in half again. Half of 1/16 is 1/32. And imagine just doing this ad nauseum. We just continue to chop this thing up smaller and smaller and smaller. And each time we get a small portion that has half of the area of the previous one. So 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. That's exactly the numbers that we're getting here. We didn't leave the square here. Everything's really being done inside the square. We're just chopping up smaller and smaller sections. So if we add up all these values, even though there are infinitely many of them, if we add up all those values, it just equals the area of the square, which is 1. So there we have it. These numbers, even though there are infinitely many, they all just add up to the value of 1. This is crazy. This is really counterintuitive. We can have an infinite number of values, which are all finite, yet when we add up these infinitely many values, they add up to a finite value of 1. Isn't that crazy? So we say that this series converges to 1. It's a convergent series since it has a finite value, a finite sum.